I'm Ted Segal, an assistant professor in the civil engineering group at Hofstra University. Civil engineering is one of a few of the majors that we offer in the Department of Engineering. And for more information about the department and all that it has to offer, I encourage you to visit the website that's shown here on the screen. And at the end of the presentation, I'll put the link up again. And now I'm going to share a few stories with you about designing and building with unconventional materials. So many of the bridges and buildings that surround us are built from a limited set of materials, such as concrete, steel, glass, and wood. And these are all materials that have well-established precedents, standards, and design guidelines. We look at the world around us and we'll see lots of examples of these kinds of materials being used. However, if we can consider a broader range of unconventional materials, they may offer environmental, economic, and/or social advantages. And so in this presentation, I'm going to discuss a series of experimental projects that I've worked on that utilize various unconventional materials. And so first I'll talk about rope bridges, then I'll talk about an acrylic pavilion called Two Blue Shells, and we'll talk about why it's called Two Blue Shells, even though it's obviously hot pink. And finally, the cast in place pavilion. So here on the screen, you see a photo of a suspended footbridge. Modern versions of this bridge type are typically made from steel cable, but historically they've been built from a whole range of materials. We have natural fibers and iron chains. So why can't we build modern bridges using other materials? Why do we have to use steel? What if we could find a material that offered advantages? Polyester rope is one potential option. It has a low cost, it's low weight, and it's really durable. It's already being used in other applications. It's used in offshore mooring. It's used in other boating applications. And here, the bridge that you see is a 64-meter span, so 210 feet, polyester rope bridge that was built in Aibud, Morocco by Engineers Without Borders in conjunction with the Peace Corps and the local community. The bridge was built back in 2013 as a demonstration project, really to demonstrate what's possible with the material. The lead designer was Ryan Woodward, who at the time was an engineer at the company HNTB, and I became involved to inspect the bridge and then also to perform additional analysis to understand the behavior of these kinds of structures. Here's an on-the-deck view of the bridge. So you can see that it's wide enough that two people could walk side by side on the structure, and the handrail is up close to your shoulder height. If we look at the bridge in elevation or from the side, here we get a sense for just how slender this structure is. It doesn't quite disappear against the background, but it's really transparent. Below the photograph, you can see a drawing. This is a drawing showing the bridge in elevation. And here you can see that someone walking across the bridge would have to traverse a particular slope. So as you walk across the structure, you're walking on the deck, which follows the curvature of the rope. And near the ends, you have to walk up this slope of about 11%. And so in a rural area, that's not too hard. We don't have to meet the ADA requirements that we would in an urban area. But one of the consequences of switching from steel rope to polyester rope is that polyester is much stretchier. It's not as stiff as steel. And so when we look at the structure and we apply the full live load, assuming that the bridge is filled with pedestrians, we see that the bridge is actually going to move a lot. It's going to shift down quite a bit because that rope is going to stretch. And what you see here is that means that at the end of the bridge, you have a really steep slope that you need to traverse. So a slope of almost 43%, you have to be quite adventurous to want to try to traverse that type of slope. So the bridge in this way becomes self-limiting in how many people can walk across the structure at one time. But of course, the alternative to designing the bridge to be self-limiting is you can put signs up to try to restrict a particular loading. So this works until it doesn't work, right? So if you decide you want to ride your horse across the structure, you come over and you deface the sign and you take your horse ride across. So as far as I know, there haven't been any camel crossings yet, but it's still only a few years old. For those of you that haven't had an opportunity to walk across a bridge like this, here is a video showing what it's like to go across with a few of your close friends. On the bridge, you'll see these little boxes. Those little boxes are what we call accelerometers. They measure how the bridge is moving. You can see the bridge is swaying a little bit side to side. We were running a series of tests to see how the bridge moved under different groups of people walking across the structure. Here's a laptop strapped to the deck, also recording some information. And so while we continue to look at opportunities to use polyester rope for these long spanning bridges in rural areas, we've also been looking at how these bridges can be deployed for disaster relief, perhaps in urban areas. But one of the big challenges is that these lightweight rope bridges require heavy anchorages. The superstructure, the bridge itself, is quite light, but then you have to pay for that at the ends by having very heavy structures that can support the cables. And what you see here on the left is a photo of that bridge in Morocco with the deck not yet in place. And you can see that the ropes come in and they're anchored back into concrete, which is then anchored into the rock. On the right is an investigation that we did on Hofstra's campus where we were looking to connect to vehicles that could deliver the bridge to site. So a rapidly deployable bridge that could be deployed, let's say after a hurricane, to rescue people or to provide a temporary reconnection within a walking network that's been disrupted. The idea is that the truck could carry the components to site and then serve as the end anchorages. We're also looking at trees and other natural features as end anchorages. And with support from the Thornton Tomasetti Foundation, we've developed a design for a 10-meter bridge that utilizes the components shown here and then can fit into 2 large backpacks. Each of these backpacks can be carried by a person to the site. Let's say that the site's not easily accessible by vehicle. You have the 2 backpacks ready to go and you hike to the site as needed. To make this work, we rely on a combination of manual drone flight and prefabrication of the bridge components. We do this because it allows us to access sites where we only have access to the first side of the crossing. So let's say you show up at a site, there's a flood, you need to get across the flooded area, but you don't have access to that far side. By using the drone, we can make a connection at the far side and then deploy the bridge. The components that you see here consist of, at the top left, we have what are called come-alongs, or they're winches. We have a number of bridge ropes in blue. The drone is shown here in the center. We have a ratchet strap, which also works like a winch. At the right, bottom right, we have a net, and that net's critical. The net serves as both the guardrails, but it also serves as a flexible deck. It's what you'll actually walk across on the bridge to get from side to side. And that's one of the key things here because that really helps bring the weight of the structure down. And here is a close-up of the drone that we use. It's an off-the-shelf product that you can buy at Best Buy or on Amazon. And below it, we have a custom 3D printed spool that my students designed. And on the spool is the pilot line that will be flown into place first. So let's see how this whole deployment process works. Here's a site out on Long Island, and the drone is on the ground, and we're assuming that we only have access on one side and not the second side. So you have to use your imagination here and pretend that the side where my students, Nick and Lori, are is the side we have access to. And then between them and the far side tree is a raging river that they can't cross. So now the drone is taken off and Nick is flying the drone. You're going to see Lori step into that imaginary river. She's not feeding commands back to Nick or helping in any way yet. She is just taking video from another vantage point. So here's the drone. It's moving forward and you can see this thin diameter line is being let out. That's the pilot line, or the initial string that we let out to help us then deploy the larger bridge ropes in a few minutes. The drone gets to the far side and flies around this Y-shaped branch configuration. And again, Lori is in that imaginary river, but just to take additional video. And now the drone is returning to the initial side. And now it has been disconnected. The pilot line is connected to a pair of larger diameter ropes that will then be used to support the structure itself. And Nick is going to pull on the small pilot line and in doing so, drag that next set of ropes around the far side tree. So here he goes, he's pulling and continuing to pull. And when he gets to the point where he's pulled one rope all the way back to him, Lori is able to clip in on the other side as well. They can connect the net in, and now Lori and Nick will pull in opposite directions. And in doing so, they're gonna drag the net across the opening. And so here they are pulling those ropes to pull the net into place. Now they're setting up to tension the bridge. So you get to the point where you can only pull so far just by hand. And so they're going to use these come-alongs to gain mechanical advantage to really tension the net and to bring it up into place. And here they are, they're tensioning the ropes. And now the bridge is finally installed. And so they deployed this in about half an hour. They probably could have deployed it even faster if they were really moving. Of course, it's easy for me to say that, standing back, watching them videotape it, but they were moving at a good pace, but this could definitely be made even faster. Here's another view of the bridge. So this is the view from the near side looking to the far side. And we deployed this at multiple sites. Here's a site on Hofstra's campus. And Nick, one of my 2 students, is walking across the bridge. Again, you can see the net is both the guardrail and the deck. You can see the deformation below his feet as he walks across. So it's a flexible deck, but it's been sized so that it won't break. It's been sized so that your feet don't get caught in the mesh openings, and you can get across it relatively quickly. Here's a video of Nick walking across the bridge. So these suspended bridges, both the long spanning ones and the short spanning deployable bridges, all depend on those hanging ropes being in tension. And tension is the pulling force. So you can imagine that you take an object and you pull it apart. The ropes are experiencing that kind of load. In the foreground here in this picture, you can see a vine. It's right over here in the front right. And that vine is also hanging in pure tension under just its own weight. And this hanging form is called a catenary. And it's the natural shape that a rope or a vine will take on under its own weight. Now, if you can freeze that form, if you can freeze that catenary form and flip it over, we're then going to have a form that's in pure compression. So compression is the opposite of tension. If tension is a pulling, compression is a pushing together. And the reason that I really like this photograph is that in the background, we can see this whole series of catenary arches that are constructed from bricks that are in pure compression. This structure is located in Barcelona. Some of you may be familiar with it. It was designed by Antonio Gaudí. Gaudí, who is well known for his architecture, often it was really fanciful. You could find the facades of his structures being quite whimsical, or in Park Güell, he had lots of mosaic tiles. He also acted very much as an engineer, and his work in this capacity is very different from his work as an architect. Many of Gaudí's engineering works, while I think are quite striking in their own right, consist of really structurally rational forms. Here you can see a whole series of structurally efficient catenaries in the background. Now, this idea can be extrapolated into 3 dimensions. On the right is a set of models developed by the Swiss engineer Heinz Isler that he created by hanging membranes, so surfaces as opposed to a vine or a rope. And then he would flip these. And this concept would inform a number of his concrete shells, like the one at the left. So this is a series of shells that was used to cover a set of tennis courts. This is a really powerful technique that I have my senior design students explore, and you can see the variation in form. So for this particular workshop, all the students were given the same size fabric, and they were told to hang the fabric at its 4 corners. And in doing so, even though they had the same prompt, everyone generated ideas that were slightly different. Now, this technique, just as Isler had done it, is generally used to create a small scale design model that could inform the geometry of a full scale structure. Right? You create the small scale model, you learn from it, and then you build something that's quite a bit bigger. The technique is not usually used to build the full scale structure directly, but what if it could be? So that was the premise of a project I worked on back in 2011. So at the time, I was working for a company, SGH, in New York City, and 2 architects approached a colleague and me with a design for a pavilion on Governor's Island. So Governor's Island, for those of you that aren't familiar, is a small island that's just south of Manhattan. And their idea that's shown here in these renderings was to create a shell structure out of a composite jute material. And they wanted to construct the shell by performing a full-scale flip. So they wanted to create a hanging model, and then they wanted to flip the whole thing and create this structure. However, with their initial models, they would hang the model and allow the top of the surface to lay flat as if obstructed by the ground. They were interrupting the natural form that would allow it to be in pure compression. And they had a really good reason for doing that. They wanted to put a band up on top of the shell. But this form is not ideal. And so we started to make suggestions about changing the form and to at least remove that flattening. And here you can see the architect went back into the kitchen and created a few new physical models. And we went back and forth a couple of times with physical models and computer models. Here at the left, you can see one of the models they made that's hanging in tension, and the model at the right that's hanging, that's been flipped over and is now in pure compression, or that pushing force. If we compare the rendering at the right, this is the revised geometry, and you can compare that to the one at the left. You can see that at the right, there's a lot more curvature. We now have pure compression. This was a largely untested material in 2011, so we wanted to make sure we could be as efficient as possible. We suggested moving the band off of the shell so that we didn't have these large point or concentrated loads on the material. We didn't win. And at the time, I felt a bit of relief because I really had no idea how we're going to pull off the construction of this. But I've been thinking about this idea of how we can flip at a large scale ever since then. And so in 2018, the International Association for Shell and Spatial Structures had a call for a competition to build a pavilion in Barcelona for their annual conference. And the team that I worked with was really interested in exploring how to reuse waste. And we focused on reusing plastics. And after looking at a number of different products, we finally settled on acrylic. Additionally, the competition required that the parts for the pavilion fit into 6 boxes. And this constraint required that we develop a discretized design. We couldn't have a monolithic shell. We had to create something that could be broken apart and easily shipped to Spain. And so here you see the concept. We're going to pin the acrylic. We're going to hang it, and then we'll disassemble, and then we'll reassemble either back in the hanging position, or we were really hoping to flip it over and have the compression shell that you see in the far right image on this slide. But acrylic doesn't behave like Easler's models, where he would pour some kind of liquid that would cure on the membrane. When you hang acrylic, it won't take the shape that's shown here in the second from the left. You need to transform the material. So let's see how that transformation occurs. So as you can see, heat is a way that we can transform acrylic. And when you heat acrylic, what happens is that it eventually passes a point called the glass transition temperature. At this point, it hasn't melted. It's just very stretchy. You can think of it like gum on a hot day. On a hot day, if you step in gum, you know it stretches for a really long time. On a cold day, if you step in gum, it's not quite as bad. It doesn't stretch as much. And so when the acrylic becomes stretchy, it deflects and forms that curved shape. And then when you cool the acrylic, you're able to lock the shape in that you want. So in addition to our home oven scale tests, which are completely safe, the temperatures that we were heating the acrylic up to are low enough that we're not creating toxic fumes. We submitted renderings like this one showing what the pavilion would look like at the full scale. So you get a sense of how big it is. This was intended for an inside environment, but big enough for a handful of people to stand below it. Others have experimented with this heat-based form finding at the small scale, but we were interested in making it work at a large scale. We were fortunate enough that our pavilion was one of the ones selected for inclusion in the symposium, and we got to work. So here we are at Plexicraft, a furniture manufacturer in New York City, going through scrap at their facility. You might have heard of Plexicraft. They've been featured in the New York Times a few times in the last few months because they've been producing a lot of acrylic barriers for office buildings. They also had sheets of this hot pink acrylic that had been left over from a previous project and that had sat so long that the adhesive was difficult to get off. At this point, the company really considered this waste. No one was coming by asking for any more hot pink acrylic, and so they donated it to us. So while we'd initially planned to use blue acrylic and we named the shell 2 blue shells, we ultimately used hot pink acrylic. So it was a good lesson in how you name your project. Here we are in Brooklyn doing a mock-up. So one of my architecture colleagues, Albert Chow, has a membership at a makerspace in Brooklyn. And here we are doing a setup. So in the top left, you can see the framework that we will have to put inside an oven. We took the large acrylic panels and we used a laser cutter to cut them down into smaller tiles that could then be disassembled. At the bottom left, you can see the full grid. At the right, we've lifted up off the ground and you can see that there is some curvature into it, but this is all elastic or recoverable. So as soon as we put this back down, it'll flatten out. We still need to add heat to transform this a lot. So how are we going to do that? Well, we needed to find a really large scale oven. And so I contacted over 20 different companies in New York City and on Long Island. And finally, we found a company whose owner not only was open to letting us experiment, but let us use his facility for a really low cost. And so here's the oven. It's an absolutely terrifying thing. It's a 9-meter long, 2.5-meter wide, and 3-meter tall walk-in oven. They usually use this for powder coating, handrails, things like that. And here's a time lapse of the process. So we're putting the frame up into the oven. Now we're bringing in that grid of acrylic. We're going to lift it up, lots of hands to make this work. Making some adjustments. Close the oven up. Now we're stress eating bagels and drinking coffee, anxiously awaiting to see if this thing is going to still be hanging or if it's fallen to the ground. And open the oven, and now you can see the dramatic change. So again, not just that elastic recoverable deformation, but really that transformation that's required to make this structure more efficient. So now we're taking measurements in the oven so that we can figure out how to set this up when we have to flip it over. And now we're doing some cleanup in the oven. The photos here are side by side of the before and after. So before, again, some deformation, but after we heat it, you can see the change in shape. And as we move around the shell, you can see that it changes colors. So before I described it as hot pink, but from this angle, it looks orange. But then we get into the oven and look out, we can see that with the light hitting in this way, it really looks pink again. Here the shell is being removed with many hands. On that day, I had a large number of students come out to help, and also a Hofstra alum helped out that day as well. Here we are disassembling the shell ahead of packing and transporting the components. Now it's been shipped to Barcelona and we're reassembling with a team there called Dubuku. Dubuku is a group of volunteers that's really interested in the built environment and helping out on projects like this and educating people in Spain. We assembled each of the 2 shells in halves, and then we would lift the 2 halves into place. Again, lots and lots of hands to help make this work. Here is a view of the shell with the halves being lifted into place. We connected to the corner of the post. I'm here connecting to the back post. And then once we had the 2 halves in place, we connected the 2 halves together along a seam to create a single shell. And then we repeated with the second shell. So here's a final view in the space. The symposium had over 20 pavilions that were all built in this ballroom, and we had about 12 hours to install. So it was a pretty hectic install. The two shells were initially supported at different locations when hanging in the oven, and as a result, they have these different shapes. And so even though we use the same method of heating the acrylic, we can make slight variations to the form just by playing with where the ends of the acrylic were supported initially. Here's another view of the final pavilion. And here's the view from the inside. So unfortunately, the space in Barcelona didn't have any natural light coming in, but even with the artificial light, depending on where you move through the space, you had different light passing through and different colors. Some of the best photos, I think, really were within the oven. Here's one after we had hung and heated the acrylic, and you can really see the beautiful local and global curvature of the piece. Now, this project investigated both waste and material transformation. So parts of my research and design work really look at what other kinds of waste and what other kinds of material transformations can we utilize. What about clay cracking? So when clay goes from being wet to dry, it shrinks and cracks. So those of you that have done ceramics are familiar with this. And usually when you see your piece crack, it's maybe time to start again. Or we might think about this in terms of drought. We see a dry riverbed and we see that it's cracked, and we think about the negative connotations that come with cracking. But what if we can actually use cracked clay as a positive? And so this was the material transformation that a team I worked on put forward for the 2017 City of Dreams competition. So again, we're back on Governor's Island, but with a different team now and hoping to win. The focus this year and all years really is on sustainability and envisioning what that means for New Yorkers. So we had envisioned using waste clay as a formwork for casting recycled aluminum. So the idea is that you would take wet clay, let it dry and crack, melt down aluminum cans, pour them in, remove the clay, take the panels out, and form the structure at the right. To give people that visited a sense of how it was built, on site we would have clay pools that would dry and crack and then re-wet over the course of the whole summer. And then the dream with these projects is to have a circular economy where afterward the materials can be put back into the city. So this is the rendering that we put forward in our proposal. This is another rendering. So the site was nice. It had a nice view of One World Trade Center in the background. We made it into the finalist stage with these renderings. And after studying past competitions, we decided that we needed to create a prototype to have a chance at winning the competition. So the weekend before the deadline, which was right after Thanksgiving in 2016, we did what everyone does, and we did some Black Friday shopping. And so one of the team members bought a propane torch in Chinatown, and we had an electric furnace delivered from Amazon, and we made this small scale casting. So we took this baking pan and poured clay in it and let it crack. And then we poured aluminum in and used the propane torch to keep it warm. And we had this really small piece. The one at the right is about the size of an internet router. And I had two students post-process this for a couple hours. Basically, they took off all the sharp edges. We figured that if anyone cut themselves on it, we wouldn't have a good chance of winning. And we didn't hear back for months. We were supposed to know in December of 2016, and we didn't hear back. Finally, in January 2017, we were alerted that we'd won the competition, and now we needed to meet a June deadline. So we had 5 months to pull this off. And at this point, this prototype was the largest piece that we had made. So this, again, is the size of an internet router. And now we need to figure out how to do this at 2.7 meters tall by 0.5 meters wide. So we had a lot of work to figure out. So we did more prototyping. We needed to figure out how to get a reasonable cracking pattern. So we looked at things like how much water should go into the clay, how should we fill the trays, how should we dry the clay. Here's a time-lapse video in which clay was pressed into a tray and then a fan was used to dry it. This was research done by my student Sayeda Manzoor. She worked with me for the whole semester and tested these different variables. So here's Sayeda working to press that clay in. Took a long time. The time lapses doesn't do it justice. And now you can see the cracked clay pattern appearing. This is a really beautiful black clay that we pulled out of Flushing from a construction site there. So we tested this method. In the end, we decided to hurry up the process by actually using a slurry, so a much wetter mix that we could pour more easily into the form. But the research that Seda did was really critical for understanding why this technique that we thought we would use, we decided to switch. We also had to collect a lot of cans. So we ran can drives at schools and with scout groups. We had the help of a group called Sure We Can in Brooklyn, and my students very thoughtfully every Monday after the weekend would leave a bag of cans at my door. We also got a boost from Sims Municipal Recycling. They donated these large bales of crushed aluminum. We created a smelter and we were able to smelt down some of the material. However, given the time constraints and scale, we were in over our heads. We could not smelt all this down with this homemade smelter. And so we ended up having to supplement what we had done with the aluminum cans with bought recycled aluminum ingots. So still recycled, which is better than virgin aluminum, but a change from what we had intended. Now we're in March, so 3 months out, and we're preparing for our first prototype. At this point, we've teamed with Scott Thompson. He's at the left in the top left photo, and then Bruce Lindsay at the top right. Two of these artists that are down at Grounds for Sculpture in Hamilton, New Jersey. They both have decades of casting experience, and we worked out of Scott's studio at Grounds for Sculpture. At the right, you can see Scott and Bruce lining up for the first pour. And here they come with the crucible. I'm the one taking the video. They're pouring in. And you can see the aluminum going into that mold. So there's the cracked clay inside there, and there's smoke coming out, and there's fire, and the aluminum's pouring right through. And these two are professionals. They're not flinching at all. I'm slowly backing away with the camera. This is the first casting that I've ever seen. Okay, so what's going on? Well, when you dry the clay, you can't get it perfectly dry like you would in a typical casting process when you use resin bonded sand. And so any moisture that's trapped in there is escaping in the form of steam. Now, the reason that you saw the aluminum pour through the bottom was we were using a low-cost wood bottom for the form, and we sprung a leak. And so we were partially using this as a chance to first test the process, but we were also trying to get a first prototype, this first piece at the bottom right here that we could use to help fund our project by showing off a proof of concept. We also ended up with these really nice articles. We have at the right, we have the wood form kind of has this same impression as the cast pattern and the top form as well. So nice little relics from the process. We were able to receive additional funding through Kickstarter after we produced this piece. Now we're in April, 2 months out from opening day. Top left, we're mixing the slurry. Top right, that slurry is getting poured into a series of wood trays. Bottom left, you can see that we have a series of fans, and the fans are left on for a couple of days to expedite the drying. And at the right, you can see 5 trays of clay that are all dried and cracked. Now, we were fortunate to receive that funding, and you can see in the top left, we've improved our steel casting trays. We have 3 of these steel trays, but that's all we could afford. We could only afford 3, and we were running out of time. We couldn't wait to just dry 3 panels of clay at a time. So to dry more at a time, we would actually dry one place, and then we would solve this huge puzzle. We would transfer all the pieces into the steel casting tray so we could do more than 3 a day when we cast. So not efficient. That is where we would improve the process going forward so we could dry directly in the tray that we would eventually cast into. But we had enough labor and we could make it work. On the left here, you can see what happens after one of the casts. You can see there are splashes on top. Again, this process is a little bit more explosive than if you were to use the traditional resin bonded sand, again, because of that moisture that's trapped in there. Now you can see we've taken the top of the mold off for that center photograph, and you can see the clay still embedded in the aluminum. We would have to knock that out and use power washers to really clean it. At the right, you get a sense of scale. This is my colleague, Josh Draper, an architect, and he's about 6 feet tall. So you can see how tall the panels are. There's still a lot of sharp edges that we have to take off in post-process. So at the top left here, you can see basically the project manager for the project and longtime collaborator of mine, Lisa Ramsberg, another architect, is using a plasma cutter. So between Lisa and myself, we probably spent about 24 hours hunched over using plasma cutters to take out some of the call flashing, where aluminum got underneath the clay and filled in some of the gaps. We also brought down an army of volunteers from the city to help out, and they used grinders and other power tools to help smooth the edges and chamfer them. And as far as I know, no one cut him or herself on the piece when it was installed. At the top right, Bruce and Scott are putting the last touches on a panel before we pull one last all-nighter and then drive everything up in a truck to Manhattan and then drive onto a ferry to take everything over to Governor's Island. We ended up installing the pavilion in under 36 hours. Here you can see we're installing one of the panels. And we worked right up until opening, and here's the realized structure. The form here was chosen for architectural reasons. We have what's known as a portal frame. It's not a form that is as structurally efficient as the hanging ropes or the shell structure. The aluminum panels in the end needed to be supplemented with a steel frame, and you can see kind of surrounding each of the aluminum panels is that steel frame. We just weren't comfortable in the end having the aluminum stand by itself, so we provided the steel structure to complement it. Here's another view of the pavilion. We had run out of budget and time to build a second one, and we were also asked by the sponsor to move our pavilion to a site farther north on Governor's Island. So we still have this beautiful view of One World Trade Center. If you look at the clay, you can see that it is wet near Lisa, and then it's dried and cracked near the pavilion. So it did what we'd hoped it would do. But it also did some really exciting things outside. Drying the clay outside introduced more variables. And here you can see these dimples in the clay. And so what would happen is it would rain, and the clay might be in what we call a plastic state, and the rain would hit it and leave these little dimples. And then when it dried, you would have the dimples preserved. There are leaf prints and footprints. We found out that there are raccoons on Governor's Island. There's tire prints, and at least one person lost a really nice pair of white shoes in the clay. Here is what we call the vandal load case, a person on top of the pavilion. So all in the service of load testing and also getting this photograph. Here you can see the cracked clay process that was used to create the aluminum panels adjacent to the aluminum. And now the steel frame, which is between the aluminum panels, serves to produce a reveal. And I think it worked out quite nicely because it differentiates between adjacent aluminum panels. After the pavilion was taken down, the panels were turned into artwork and furniture. At the left is a photo from an exhibition in New York City. During a performance, the panels were tilted down and plaster of Paris was used to capture the panel's negative on the floor. At the right is a stool made from cutting down a panel. Stools, benches, and full-scale panels were all Kickstarter rewards that we used to fund the project. These experimental projects involve a lot of work. I tried to name a few of my collaborators throughout the presentation, but there were many more. The collaborations occur between engineers, architects, artists, and of course, students. Here in this picture are a few of my colleagues, but also a number of students that helped on the project. 11 students in all helped, which was invaluable. At Hofstra, we really have some incredibly talented and dedicated students that are interested in the different ways that research and design intersect on the way to getting something built, right? These aren't purely research projects. They're not purely design projects. They really are at the intersection of these two things. And the students really enjoy and want to learn through making. And we've been fostering that at Hofstra. It's really easy to take for granted that our infrastructure has to be built in a certain way or with certain materials. We look around us and we see wood structures and concrete structures, glass structures, steel structures. But I think if we can stay curious and if we can remain open to new and different ideas, then there are a lot of opportunities. We really have a chance to learn from some really unexpected and to complete some really exciting work. So thanks again for your time and attention, and I'm happy to take any questions you have. Feel free to unmute yourself and to ask your questions directly, or if you feel more comfortable using chat, I'll answer stuff through chat as well. Thanks. Okay, so there was a question from a while ago. I'm sorry, I missed it during the presentation. So one of the questions was, please repeat the name of the material. I think that was back with the bridges. So the polyester rope was being used for the bridge, and then the net itself in the larger structure was in the deployable rope bridge was also a polyester rope net. And Richard asked, is there a floor on the deck? And so for the rapidly deployable structure, the net itself was essentially the deck. For the bridge that was built in Morocco, there was a wood deck there. other questions that I can help answer? Great. So Kathleen asked, how do you see these as closing the loop in terms of manufacturing and use of materials? That's always the challenge now, the idea of having a circular economy and how we can use this, and also how can we intercept waste. I think maybe I'll address the part about just how we intercept waste and how that works in terms of the material life cycle. We tried to reuse aluminum cans, and where we intercepted the waste wasn't really the right place. We probably should have done it later in the process after it had been processed back into aluminum ingot that we can more easily utilize. For the acrylic, we were able to intercept it and use it in a form that was pretty well already something that we could work with. So I think part of using waste materials and things like that is understanding where in the process you kind of intercept it and thinking about these at kind of a larger scale. These are industrial scale processes. The idea of how do you disassemble and reuse materials at the end of the lifespan is really interesting. I think part of it is you have to think about disassembly and how are you bonding materials together and connecting them and making sure that when you do take them apart, they can be reclaimed. So that was one of the advantages for the cast in place pavilion, is that when we took apart the panels and the steel frame, everything could then be broken back down into its constituent materials. Same thing with the acrylic pavilion. So I think a lot of it is thinking through how do you make sure the materials can be separated at the end of the life. So Richard asked, for the third project, what was a practical use other than as art? Right, so the aluminum pavilion project was intended as a place where you could rest and relax and serve as there was shading. So I know you think with the openings, how are you producing shading? But we did studies to try to correlate the crack pattern to make sure that we had structurally enough aluminum to support itself and that vandal load of people on it, and also to have a dense enough crack pattern that we could produce particular shading patterns. And so we've also been talking about how this might be able to be used on the vertical panels, and could we create a variation in the crack pattern to further help with shading. And so I think there's a lot of work there that could be done in that respect. Other things that you could do with this is possibly cast materials into the holes between the aluminum to create surfaces that are then potentially watertight. So there's other applications beyond what we've done here. We're also wondering if maybe it could be used just purely as furniture as well. Question from Carla: has the polyester been used in walking bridges in other countries such as Costa Rica? That's a great question. I don't have an exhaustive list of where different materials have been used. In general, polyester rope has not been used extensively for bridges. The most common material now used is steel cable. There are non-government organizations such as Bridges to Prosperity and Helvetas and Bridge the Gap Africa that work in different areas. I know that Bridges to Prosperity works a lot in Latin America, and we're trying to team with them to potentially work on a project in Bolivia in the future, but that would be a steel cable structure. I think there might be some examples of polyester rope and synthetic rope projects at places like rope courses and things like that, but they're not frequently used for structures like the one that I showed here. But they would be well suited to different environments like that. How energy intensive is the process of converting the aluminum cans to ingot? We were doing it in a very poor way. We were doing it in a way that was very energy intensive, and that in the end is why we backed off. So again, it seems like it should be easy to convert aluminum cans back into ingot, but the reality is that the aluminum cans also have other things on them. So there's liners, and there's mixed in with the aluminum cans where takeout containers. To actually convert that back into ingot is really an industrialized process. And that's why trying to get that at that stage as opposed to the cans would be better. So if we look at the industrialized process, I don't know the numbers off the top of my head in terms of how energy intensive that is. But if you use recycled aluminum in a project that's already been converted, that let's say you take virgin aluminum, so it's never been used before, versus recycled aluminum, it's 8 to 9 times less energy intensive to use that recycled aluminum. So once it's been reused one time, it's a lot less energy intensive. These are great. Other questions or follow-ups on the ones if I didn't get them. Carol's asking how durable the material is used over time. That's a great question. So the polyester, that's one material that people frequently ask about, is durable in some respects. It works well when it gets wet. It doesn't have the same corrosion issues that you see with steel. At the same time, UV becomes a potential issue, and so we use a particular polyester rope that has coatings in it to help extend its life. There are also covers on top of the ropes to prevent direct UV exposure. The bridge in Morocco has 10 ropes total, 3 at each handrail and 4 below the deck. And so this is in contrast to a lot of steel cable bridges where maybe you'd have 2 at each side at most. And what this allows us to do is to take 1 rope out at a time and then replace it as needed. So let's say that the lifespan of a polyester rope is, and we're not exactly sure, so it's being monitored, 20 years. You could take one of these out before then, and you could slowly take out each rope individually and replace it. And so by the time you get 40 years out, all the ropes are different. But the bridge has never really had to be taken out of service for longer than 2 or 3 days to replace a single rope. This also has allowed the group from Engineers Without Borders to take ropes out of service and to test them to see how they've been performing, to understand when they were to build another bridge, how that works. Acrylic is another plastic material. And again, it has some issues at elevated temperatures. So better used indoors, and you get some discoloration over time. The aluminum itself is quite durable. One of the issues that we ran into is that when we cooled down the aluminum, we weren't able to do that in a controlled way. If you actually heat treat the aluminum and kind of heat everything up to the same temperature and then cool it, you have a product that's what we call more ductile. It doesn't break as suddenly if there's a fracture. And so we were left with brittle aluminum. And so that could be problematic if there were to be an impact against it. Okay, I think if there aren't any other questions, I will leave it here. But feel free to reach out to me. My email address is on the screen. If you have other questions about Hofstra engineering, feel free to visit the website. And again, thanks so much for your time. I really enjoyed talking to you, and the conversation and discussion afterward were great. I really appreciate all the questions. Take care.